And so today we're going to look at the principle of spectroscopy. So in our last class, we started with introduction into instrumental method of food analysis. And if you recall, among the principles that were mentioned as one of those principles that we use in instrumental method of food analysis, spectroscopic techniques is one of those principles. And so today we're going to start with spectroscopy. So what is spectroscopy? So spectroscopy is a study of how matter interacts with light. All right, and by light we mean electromagnetic radiation. So is basically the study of how matter interacts with light. So there are two players in this definition. We have matter and then we have light. So we all know what matter is, right? Yeah, so and then light, and I said by light we mean electromagnetic radiation. So every light, of course, any light it's a radiation. So depending on the region at which they occur. So now when we talk about study, we mean we're going to be looking at the production, the measurements, and the interpretation of spectra that arises from this interaction. So you could also think of it in this way, spectroscopy, you could think of it in this way, like when you have a juice in a cup of water. I mean, you have a juice in a cup, and then you really want to analyze the concentration of, let's say, vitamin C in that juice. All right. So you can pass a source of light through that cup, and then the cup absorbs the light, and then some other part of the light goes out of the cup, which is emission, and then you measure the intensity of light absorbed, and then you can deduce what the concentration of um, vitamin C in that juice that is located in the cup. And so basically that's what we do in spectroscopy. We study the interaction. Now you have shine light on the juice in the cup. Now the light has interacted with the juice, and then some other part of the light goes off the cup. And then so what you're doing is to study the interaction, what happens, what amount of light goes into the cup, what amount of light goes out. And by doing that, you get to know some certain information about the contents that is in your cup. All right, so the interaction between AMR and light is what is known as spectroscopy. That's the study or the science of how matter interacts with um, light. Now, there are some words that are somehow interchangeably used. Now we have spectroscopy, we have spectrometry, and then we have spectrophotometer. So these times, what they mean is, of course, spectroscopy, as we have said, is just a study, right? The study of the interaction between light and matter. So by matter, it could be liquid, it could be solid, it could be gas, but mainly what we mean here is molecule and atoms. So the substance are more in a molecular form or atomic form in this case. Now, spectroscopy is just a study, like we highlighted earlier, and then spectrometry is just the measurements. All right, the science of measurement. How do we measure the intensity of the light that goes into the matter or into the substance? So that is spectrometry. And then spectrophotometer is the equipment So the equipment, you can think of it as the hardware, as a device. And so when you hear UV visible spectrophotometer, so you know they're talking about the equipment. All right. So spectrophotometer is just the equipment. So these are what these three terms actually mean. And so right now, just the importance of spectroscopy. Yeah, so why spectroscopy? Why do we have to do spectroscopy? You recall that in our introduction, when we're trying to classify classical methods and instrumental methods. And then we said that instrumental methods are methods that involve the use of instruments. And so what we do basically in spectroscopy is an instrument that analyzes, okay, substances. So what spectroscopy do is it can measure, it can do both qualitative and quantitative tests. And then what it does basically is it can tell us the concentration of substances, like the cup of juice analogy I gave earlier. So it can give us the concentration of vitamin C in our juice, all right, just by shining a particular source of light to the cup, to the juice in the cup. And then the machines, there's a detector installed in the machine. It detects the amount of light that comes out of the juice, and then it computes, and then it tells us the concentration of vitamin C, for example, in our juice. So it can measure concentration of certain food compounds, you know. So it can identify content. Yeah, it can check the quality and safety of food. So it is also used in quality control of food. So, you know, these are just few from what you can use spectroscopy to do. All right, so you might be working on water. You want to determine the minerals, the heavy metals, even in your food. All right, so these are things spectroscopy could do. They can analyze and determine the heavy metals, the minerals available in food, you know, and we use all of this data in quality and safety of food. So these are importance of spectroscopy. So now let's talk about some key factors um, or some key players in the study of spectroscopy. The first one here is the nature of the species to be analyzed. All right, the nature of the species to be analyzed. So, like I said earlier, when we're talking about matter, all right, so the species could either be in atomic form or a molecular form. All right, so this is what we mean by the nature of species. That's the nature of the sample we are trying to analyze. All right, so we also have the type of radiation matter interaction. So the type of radiation matter interaction here would mean if what is the interaction between the light and the matter, is it an absorption process that is taking place, or an emission process, or a diffraction process? All right, so these are also very, very important. And you so for absorption, absorption is just we're going to get there. We'll talk more about absorption and emission, but you know, absorption is just when it absorbs light, all right, and emission is just when it emits light, all right. While diffraction, it's you know, when the light gets diffracted, like when the light when it bends, or kind of when the light meets with a substance, and then it bends a bit. Okay, so that's the that's diffraction. And so all this gives information about quantifying our substances. All right, so the third one is region of the interaction. Now, I was talking about shining a light into a cup and then taking measuring the amount of light that goes out of the cup. In most cases, it's not that easier. It's just an expression of it's just an analogy for you to have a picture of what we're talking about here. So in some cases you don't even get to see the light. So we have different regions where the interaction take place. We have visible region, we have ultraviolet region, we have infrared region, we have radio waves, we have x-ray region, we have gamma region. And so the one you get to see, of course, is just a visible region where you're able to see that yes, this is a light. In most cases, you don't get to see them. So these are the three important factors in spectroscopy, which we need to know, before we get deep into spectroscopy. Now talking about the region. Let's talk the region. The region has to do with the electromagnetic radiation. And so electromagnetic radiation is very important here. It's more like the major key player in spectroscopy. And so we're going to take a while to discuss about electromagnetic radiation. And, so we're going to talk about the characteristics of electromagnetic radiation. What is even electromagnetic radiation? All right, so AMR exhibits a wave-like properties that consist of oscillating electric and magnetic fields that are perpendicular to each other. All right, so now this definition tells us that it tells us that it is a wave-like properties that consist of oscillating electric and magnetic fields. And of course, you will agree with me that is where the name electromagnetic comes from. All right, so it's a combination of magnetic field and electric field. Right, so AMR exhibits a wave-like properties that consist of oscillating electric and magnetic fields that are perpendicular to each other. So this is how it works, right? So this here is a typical example of a wave, all right? And it oscillates this way, all right? So this could be the magnetic field, and you could have the electric field. You could also have the electric field to also run this way. You could have something like this, you know so that's what we mean by oscillating electric and magnetic field. So if this is the magnetic field, so this is going to be the electric field. I hope that is clear. But for to better explain this, I'm going to take away this other one. So that is it about when they talk about oscillating and when they talk about electric and magnetic fields. All right. So now there are some key features of EMR. The first one is the wavelength. All right. So the wavelength is basically the distance between um, wave peaks. All right, and the unit is in nanometer. Now, when we say the distance between wave peaks, this is what that means. These are wave peaks, right? These are wave peaks. These are wave peaks. These are wave peaks, right? So the distance between this and this is what? Is what is known as what? As a wavelength, all right? And this is the unit of wavelength. So the distance between this and this is one wavelength, all right? And the distance between here and here is another wavelength. All right, so the distance between peak is known as a wavelength. Now, frequency. The frequency, in some cases, the symbol for frequency is denoted with small letter f. You see it in some book as small letter f, but here we're using small letter v. All right, So the frequency is the number of circles per second. All right. So the frequency is the number of circles per second. So how does that relate to this structure of wave that we have here? So the frequency is the number of circle per second. So what that means is from this point, all right, to this point, it's half a circle, right? And so from this point again to this point is another half a circle. So the number of circles per second. So if a wave move from this point to this point is able to make one circle, is that right? If it moves from this point to this point, that will be one circle, half a circle and half a circle. All right, so that makes one complete circle. And so the time it takes for that wave to move from this point to this point is the frequency, all right, in seconds. So if it takes the wave to move from this point to this point in 1 second, it means the frequency of that wave, all right, is 1. All right, so that is it about frequency. The number of circles the wave is able to make in 1 second. All right, so that is frequency. All right, so now let's talk. Our frequency is clear. Now let's talk about amplitude. Amplitude A, and now the unit of frequency should be in hertz. All right, hertz or per seconds. All right, hertz. Now let's talk about amplitude. Amplitude is the maximum magnitude of the electric vector. So amplitude is just the you can just think of amplitude as the height of the wave. All right, the height of the wave. So I'll give you an example from this. So magnitude is just the distance from this point. Magnitude is just the distance from this point to what? To this point. All right, so that's the magnitude, the distance from this point to this point. That is the magnitude. While the velocity is the distance traveled per second. All right, so velocity c is what? The distance traveled per what? Per second. So velocity is just the distance traveled by the wave. All right, so when the wave starts the journey from this point and it ends at this point, so the distance from here to this point is the velocity in seconds. So how long does it take this wave to move from this point to this point? So that is the velocity. So the distance traveled per seconds is the velocity, and the energy is just how strong the wave is. All right, how strong the wave is. So when the wave moves faster, you want to believe that it has higher energy. And then the relationship between wavelength and frequency is given by this formula here. This is the relationship between wavelength and frequency. And then the relationship between energy and frequency is also given with this formula. All right, so from this formula, from the first one, which shows the relationship between frequency and wavelength, you agree with me that the higher the frequency, the lower the wavelength. All right, by the time you make let's say you're making the velocity the subject of formula, you're going to have velocity is equal to what? C over lambda. So you're going to have you're going to have we're making velocity the subject of formula. We're going to have velocity to be equal to what? Velocity will be equal to what? C over what? Lambda, right? So this tells us that when velocity is increasing, when frequency is increasing, the wavelength is reducing. All right. The same thing applies when wavelength is increasing, the velocity is reducing. So they are inversely proportional. While in the case of relationship between energy and frequency, as the energy is increasing, the frequency is also increasing. They are directly proportional. All right, because C here is the is constant. It is the velocity of light in a vacuum. All right, so it's constant. The same thing, H here is constant, is the Planck constant. All right, so the direct energy is directly proportional to the frequency, while frequency is inversely proportional to the wavelength. So I'll give you a clearer example of that. And so this is what you have. Let's say we have a wave that moves this way. So take a look at this wave. Let's say the wave moved this way. You know, it kept moving, it kept moving, it kept moving. Okay, it keeps moving. It becomes bigger, become bigger, become bigger, become bigger. All right. So let's say it continues to move this way. All right. So pardon my drawing, my sketching. And so if you look at this side, all right, and this point, you realize that the wave is moving in a different frequency here compared to here. Now, if you recall what we said about frequency, we said is the number of circles per second. Now, from here to here is one circle. All right. Now, these are half circles. This is half circle. This is half circle. So this is the point where this wave moves a circle, right? So the distance from here to here is one frequency. But if you look at this place, this is one circle. This is one circle. So the distance from here to here should be one circle. This is half a circle. This is half a circle. The distance from here to here should be a circle. So you will notice that the distance from here, okay, is higher from the distance, you know, compared to distance from here to here that forms one circle. This is one circle, this is one circle. All right, so that is frequency for you. The frequency is a number of circle per second. Now this is one circle, this is half a circle, half a circle. This is one circle, but higher what it takes higher time. All right, so higher distance to complete one circle, while in this case it takes lower time to complete one circle. So the frequency is high. It's able to complete more circles at less time here. All right, while here it can only complete a circles, you know, with more time. That is frequency. Now take a look at the wavelength. We said the wavelength is the distance between peaks. Now the distance between here and here. So here you will recall now that the frequency is high because it will produce more circles in a second. But here it will take time to what? To produce more circles. So the frequency is low. And in this case, we have the wavelength as the what? The distance between wave peak. So the distance between here, this peak, and this peak, you know, is low compared to the distance between this peak and this peak. It's high, right? So why the frequency is high here, the wavelength is low. That is why it is what? Inversely proportional to each other. Why the frequency, in this case, why the wavelength is high, the frequency is low in this case. All right, so that should give you why we have that's the relationship between frequency and wavelength. And if you look at it, the energy is directly proportional to the frequency. So the energy is higher because it's able to move faster. All right, so here the energy is getting low. Is not able to move as fast as possible to produce more circle. Do you get it? So that is why the energy is directly proportional to the frequency. The energy is higher, so the frequency is also high. So that is it about the um, the energy, frequency, and then wavelengths of electromagnetic radiation. I just hope that is clear. So that's that is it, and this formula are very important and very crucial in the principle of spectroscopy. All right, so most of the instruments, you know the principle of most instruments are based on um, this formula. All right, so um, now let me give you a clearer picture of what we're talking about. All right, electromagnetic spectrum. So now, talking about region at which the interaction take place. So we have these are the regions. We have these regions here. We have the gamma ray. All right, we have the X-ray, gamma ray region, the X-ray region, the ultraviolet visible region. We have the visible region, and then we have the infrared region. Then we have the microwave region, and then we have the radio wave region. So now, if you look at, take a look at, take a look at, take a look at these waves. All right, I'm sure you're seeing these waves. Take a good look at the waves, and then I'm sure you should be able to relate it with the explanation I gave earlier. So look at the gamma ray. So it tells you that gamma ray has higher energy, right? You can see the movement, high number of circles in few seconds, and then the wave is able to move faster. So gamma ray have high energy, high frequency, and low wavelength. All right, so the wavelength for gamma ray is less than 0.01 nanometer. All right, and the energy is very high. So you can see as it goes down the line, when it gets to X-ray, the frequency reduces. All right, and then you have the energy reduces also a bit. All right, and the wavelength also increases, and so the wavelength here is is between 0.01 nanometer to 10 nanometer, while we have for ultraviolet region, we have the wavelength to be from 10 nanometer to thing is 400 nanometer, and here is from 400 to 700. All right, so as it goes down this line, the energy reduces, the frequency reduces, and the wavelength what increases. I hope that is clear. So now let's talk a bit about this region. All right, the what? The visible region. So this is the visible region, the region that is visible to human eye. That's why it's called the visible region. All right, it's visible to human eye, and that is why it's called the visible region. So what happens there is like I've been making analogy with light here is because that is the region where our naked eyes can see. So it doesn't mean the whole of AMR falls under visible. No, we have a whole lot of them, as you can see here, but it's easier for you to understand when we're talking about visible, when we talk about things we can see. And so this is visible region, and it ranges between 400 to 700 nanometer. All right. So in this region is where we were able to see, where human eyes are able to see. Now, um, I think it's worth it to note or to mention here that we have various colors under this region, ranges from red. So okay, so it's called right, I think it's called okay, what is it called now? Okay, is it Roy? Right? Roy, uh, okay, G, blue, okay, I think this, all right. So these are referred to as rainbow color. So it's called Roy gift, right? So red, orange, yellow, green, blue, indigo, and violet. All right, so these colors falls within this range, right? And so in most cases in the laboratory, the analysis we do that has to do with identification of color are done in this region, visible region. So the instrument that that works in this region mainly is known as colorimeter. That's an instrument we use in analysis of color to determine the color of substances in the laboratory. So it's called colorimeter. So it works between the region of 400 to 700 nanometer. All right. So now when we have when you see a red color, so what that means is the frequency of light that is reaching your eyes at that particular time is the frequency of the red light, and that is why you're seeing the substance as red. When you see a green light, that's because the frequency of light that is reaching the receptors. All right, we have our eyes are equipped with receptors that are able to identify colors. All right, so it means that the frequency of light that is reaching the receptors in our eyes at that time is the frequency of green light, and that is why we're able to identify that color as green. Same thing with blue, all right? But the receptors in our eyes can only identify three colors: red, green, and blue. They can only identify the frequencies of these three colors. So the question is, how are we able to identify yellow, indigo, violet, and even orange, right? Oh, well, that's I think that is our brain in action. So, but what actually happens is so when you have a mixture of color, let's say yellow, um, maybe you have a mixture, the frequency of green light and blue light when they come together to the receptors in your eyes at various degree. All right, so your brain could just interpret it as yellow. All right, so that's what actually happened. So more like other colors, okay, red, green, blue are more like foundations of other colors. All right, so the basic thing here is our eyes are just able to identify, receive receptors of the frequencies of three colors: red, green, and blue. And then in some cases, depending on the degree or the amount of frequencies of these three colors that are reaching our eyes, we're able to identify other colors. Now, what about white and black? All right, so white is not a color. Black is also not a color in the real sense. All right, so yes, I know we have black color, we have white color, but in the real sense, black and white are not colors. All right, so what happens in the case of white is you have when we have these three colors coming together in the in coming together in the right or the or equal amount of degrees reaching our eyes at the same time. All right, so we see it as it appears as white. All right, and then when we have and so when no receptors, all right, when no frequency is reaching our eyes, all right, we see it as black. So black is the absence of color, really, while white is the presence of the three primary colors. All right, the three colors. So that's just a bit about visible, and that's just a bit about visible region. So now we are going to talk about uh, so now I think we've had enough about the EMR, the electromagnetic radiation. So it's a key component in in spectroscopy, and we need to get a good understanding of that. Now let's talk about absorption and emission. All right, so this is also very important. This it's good we have this background on how matter is able to absorb light and how matter are able to emit light. All right, so we're going to talk about absorption and emission. All right, so talking about absorption, we said this occurs when light hits a molecule or an atom, and the molecule absorbs the energy and moves to an excited state. All right, so of course, when light hits a substance, a molecule, or an atom, all right, when light hits a molecule and an atom, it moves from the ground state to the excited state. All right, so that is just absorption. But there are some few things we need to understand in this absorption. All right, so let me give you an analogy of that again. All right, so let's assume you are in a room alone, silent, in a quiet room. All right, so and suddenly somebody begins to play music. All right, so you're quiet, you're just lying down, and then suddenly somebody begins to play music, and then the music continues to play until the music gets to, you know, gets to move you, and you begin to feel the music to the point that you started dancing. All right, so it's saying that you have moved from a ground state that you were into an excited state. Now you're dancing, you're excited. So why? Because you have received adequate amount of music that is able to make you excited. All right, so that's just an analogy of how absorption process takes place in spectroscopy. So the substance, the molecule and atom must receive adequate amounts of energy from the AMR for it to be able to move to the higher energy levels. So we have different energy levels. It might move from the ground state to the first energy level, and then it moves from the ground state to another higher energy level. All right, so it's important here to know that the amount of energy, I mean the right amount of energy must be provided for the atom or molecule to be quantized, all right, that is to move from the ground state to what? To higher energy levels. I hope that is understood. So in some cases you might just be in the room and the music starts to play, and the music doesn't just get, you don't just feel the music, so you don't get excited. All right, so it means that the right, you know the right type of music, and of course the right amount of music must be played to get you excited, to get you to the dancing state. All right, so the same thing applies with absorption. So absorption is a process where light hits a molecule and then it goes to the excited state. Of course, every molecule are in the ground state before they move to the higher energy levels. And then, of course, the energy must be quantized. That is, it must receive the right and adequate amount of energy before it can move from the ground state to the excited state. Now, let's talk about emission. And so, basically, emission is just the opposite of absorption. All right, so it's the reverse of absorption, where um, energy is being released from an excited matter, from an excited atom or molecule. All right, so that is just emission. And so now the process at which that excited molecule or atom releases or goes back to or releases or get relaxed, um, there are two processes involved. The first one is what we call non-radioactive decay. All right, and this involves the transfer of energy from an excited molecule to the environment in the form of what? Kinetic energy. Okay, so the transfer of energy, okay, the transfer of heat energy. So please, the transfer of heat energy from an excited molecule to the environment in the form of kinetic energy. And so the non-radioactive decay, what it does, it releases heat, all right, to the environment through um, kinetic energy. All right, so what it absorbed is energy from light, but when it's going back to the relaxation state, when it's getting relaxed and going back to the ground state, it releases this energy in the form of heat into its environment through kinetic energy, So that is non-radioactive decay, while radioactive decay is the release of energy in the form of light. So it releases the same amount of energy that takes it to the excited state. It releases that same amount of energy to get back to what? To the ground state. All right. So this is where we're going to stop today, and then in our next class, I think this has given us a good background on an overview of spectroscopic techniques. And so in our next class, we're going to be talking about the instrumentation of spectroscopy. The instrumentation, we're going to be talking about equipment and instruments that run under spectroscopic techniques, and we're going to deal fully in two of those instruments. Particularly, we're going to be talking about UV visible spectroscopy, and then we're going to be talking about UV visible spectrophotometer, and then atomic absorption spectrophotometer. So those are the two instruments we'll be talking about, their instrumentation, the principle at which they operate, okay, the principle at which they work, and then what they can do, what they can analyze, So these are the things we're going to be talking in these instruments in our next class. And so this will bring us to the end of this class. If you have a question, please feel free to drop your question in the comment section. We'll be there to respond to your questions. And please don't forget to like and give a thumbs up to the video. Thank you. See you.